Hello, today we're going to talk about how to simplify square roots. So the title for your notes is Square Roots and Simplifying Radicals. And so that we understand, when we say radicals, we are referring to square roots. Remember, this is a video, so you can pause it so that you can get the notes and make sure that you don't miss anything. A radical sign is a square root sign, and it looks like this. A radicand is the number of variables under the radical sign. So we will try to use the proper terminology as we talk about radicals and the things under it, which are the radicand. All right, now that when we talk about radicals, we need to be familiar with prime numbers. Remember, prime numbers are numbers that are only divisible by 1 in itself. So some examples are 2, 3, 5, 7, 11, and 13. Now, the reason that we need to be familiar with prime numbers is because of trying to put radicals in simplest form. Now, we'll know that radicals are in simplest form when there are no perfect square factors other than 1 under the radical, and we're going to talk a little bit more about that in a second. There are no fractions are under the radical, and no radicals are in the denominator. So if all three of those things are taken care of, then you know that your radical is in simplest form. So one thing that we're not going to talk about in this video that you should be familiar with are your perfect squares. So for example, the square root of 4, the square root of 9, the square root of 16, the square root of 25. You should know all of those perfect squares by heart. It is recommended that you know probably up to 20, at least up to 20 of your perfect squares. And we can talk more about that if needed. Now, factor trees. We're going to use prime factorization by doing factor trees. I don't know if you remember that, but basically we're going to take a number and we're going to figure out what can I multiply to get that number and kind of make our little tree diagram like we did back in middle school. So if we have 45, I look at 45, I know I can multiply 9 times 5. 9 times 5 will give me 45, and then I look at those two. Which one of those still have factors? 5 is a prime number, so I don't have to break that down anymore. 9 can be broken down into 3 times 3. So there, I now have my prime factors of 3, 3, and 5. If I look at the end of my little branches that I made, those are the 3 numbers that I have. So when we're talking about simplifying a radical, if we have the square root of 45, we just said that 3 times 3 times 5 will give me that. So now what we're able to do is when you have a pair, bring the number out. So if you look here, we have a pair of 3s. So we're going to bring that number out as a pair, so only one time. That pair comes out as 1. And so now my answer is 3 on the outside, and I still have 5 underneath the radical. And that is how you simplify radicals. So let's look at another one. If we have 98 and we want to do our factor tree for prime factorization, we're going to say, well, when I look at 98, it's an even number. I automatically know it's divisible by 2. And 2 times 49 is how I get 98. So 2 is a prime number, so I can't do any break down 2 anymore. And then 49 can be broken down into 7 times 7. So, and 7 is a prime number, so there's nothing else I can do to that. So my prime factors for 98 are 2, 7, and 7. So if I look at this one, and if you look at this one, I threw this in there for a reason. There's a negative sign in front. If there's no number there, we can treat that negative sign like a -1. And that's going to be important here in a second. So now we have the 2, 7, and 7 underneath the radical. We have this negative sign out front. Now, going with the same thing we've said, I have a pair of 7s. And so we have a pair of 7s. We are going to bring that out. And basically, we have to multiply by whatever is out there already. So because we have that negative sign, we treat it as -1. So we're going to do 7 times -1. And that will give me -7 on the outside. My 2 stays underneath the radical. So I have -7 radical 2. All right, so if we have the square root of 48, square root of 48, we would break that down. If we do the prime factorization and do the factor tree for it, I would probably start with 2 times 24. And then when I have 24, I would do 2 times 12. And when I have 12, I would do 2 times 6. When I have 6, I would do 2 times 3. And when I put it all together, I have 2 times 2 times 2 times 2 times 3. Okay, now this time, I notice I have more than one pair. I have that set of 2. I'm going to bring that one out. Then I have that set of 2. I'm going to bring that out. Now, if I'm bringing 2 different pairs out, what am I going to do to those 2 numbers? That is correct. We are going to multiply them together. So 2 times 2 is going to equal 4. And so our answer is 4 radical 3. And the 3 was left underneath the radical, which is why that's the only thing left there. All right. So if I have 2 radical 45, go ahead and pause the video and try this one and see if you can get it right. Okay. When I do 45, I can do, I did 5 times 9, and then 9 broke down into 3 times 3. So I have 3 times 3 times 5, and I have a pair of 3s. So I brought it out with the 2. 2 times 3, radical 5. When I multiply 2 and 3 together, I get 6 radical 5. Try these 4 on your own, and then check your answers. Okay, number 1 is you should have gotten 2 radical 5. Number 2, you should have got 8 radical 10. Number 3, you should have got -3 radical 11. And number 4, should have got 6 radical 3. If you don't understand one of those, make sure you ask me or one of your classmates for assistance, and to make sure your questions get addressed. Now we're going to talk about variables as radicands. So when you have variables, you have to look at the exponents. Okay, if you have an even exponent, you're going to take half out, and there'll be nothing left under the radical as far as that variable goes. And we're going to do some examples of these as well. And then when you have an odd exponent, you're going to leave one under the radical and then take half of the rest of them out. Okay, and we're going to leave one under it so that we're left with an even exponent, and then we can take the rest of the half of those out. Now, some examples of that. If I have x to the 6th power underneath as a radicand, well, that's an even number. Half of 6 is 3. So my answer is x to the 3rd. And if I look to the next one, I have y to the 15th power as my radicand. It's an odd number, so I'm going to subtract 1 and leave that 1 underneath it. And that will leave me with 14. And I want to take half of that 14, which is 7. So y to the 7th is going to come out, and the y will stay as a radicand underneath the radical. So y to the 7th radicals y. All right, 1026 is an even number, so I'm just going to take half of it. I'm going to get a to the 513th power. And then this next example, we have b to the 783rd power. That is an odd number. So I'm going to subtract 1 and get 782. And then I'm going to take half of 782 and I get 391. So I have b to the 391st power, radical b. All right, try this one on your own. A to the 13th is an odd number, so I'm going to leave 1 under and take half of the rest. So I'm going to have a to the 6th out. B to the 24th is a even number, so I'm just going to take half of it and bring it out. So I have b to the 12th out. So my answer is a to the 6th, b to the 12th, radical a. All right. Now, on this one, you have a number and you have variables. You treat them as different, almost like a different problem. You do the radical 18, just like we did the first examples we looked at. And then you do the C, and then you do the D. So try to do that one, and then we'll show you the answer. And you get 3c squared, d squared, radical 2c.